Hello, welcome to Chapter 15. This week we'll be covering Chapters 15 and 16 in our lecture videos. And we're going to start with this video, which will go over just Section 15.1, which will cover a lot of the terms that we're going to need to be thinking about as we continue on in this chapter and the next. So, to start out with, the goal of this video is to make sure we understand what the different layers of the sun are and what makes them unique from each other. Now, if we've ever looked at the sun briefly, even though we know we're not supposed to on a nice clear day, it's just a really bright light in the sky. And we know that it's too bright for our eyes to look at. But if we take a picture of the sun with a spacecraft, like on the left, or with a camera, like on the right, what we're actually seeing is what's called the photosphere. It's often referred to as the surface of the sun, but it is not a solid surface. The sun doesn't actually have a solid surface the way the Earth does. Instead, it's just a really large ball of gas and plasma. So we'll learn about that word plasma in just a little bit. But the so-called surface of the sun is the difference between what we're able to actually look at. We cannot look any deeper than this, and what we are able to look at, the outer layers, which we'll come to eventually. But beyond just looking at the sun, and we can see those dark spots on the picture on the left that are called sunspots, and we'll talk about those more over the next video and the one after. But when we're looking at the sun like this, what we're seeing is the place where the sun's blackbody radiation is finally able to freely flow outwards away from the sun. It's the part of the sun that we refer to when we talk about the temperature of the sun, even though there's lots of different temperatures below and above. It's the photosphere temperature and color that we associate with the sun. The fact that the sun is a yellow star is because the temperature at that location, at the photosphere, is not too hot because it would look blue if it were hotter, and it's not too cold because it would look red if it were colder. But we know that that radiation, that blackbody radiation that's being emitted, is not just a continuous spectrum. We've already talked about the fact that the sun makes an absorption spectrum back when we introduced that idea in Chapter 5. Now, what we have talked about is the fact that this set of dark lines in the rainbow spectrum can tell us what elements are present. We can compare to the different patterns that we see in the laboratory and determine that there's hydrogen there, and there's helium there, and oxygen, and iron, and all these sorts of different elements based on their spectral fingerprints. What we have not yet talked about, and we won't go into detail of, but what we haven't talked about yet is the fact that these spectral lines are not all the same width and depth. If we look at this picture, we can pick out certain lines that are more obvious to us because they're darker or they're wider, and some that we can barely even tell are there without zooming into the picture more. The strength of those spectral lines is actually telling us about how much of that atom or molecule is present in the layers of the sun, rather than just whether it is or isn't there at all. It's complicated physics, and we're not going to go into the detailed math behind this process, but what is really important to note is that the first person to do this complicated math and physics was Cecilia Payne-Gaposchkin. She was actually the first woman to receive a PhD in astronomy in the entire US, which was only back in 1925 and not sooner. And her dissertation, the research that she did, focused on understanding that complex physics behind the relative abundances, how much of each atom there was. What she found was that the sun is about 75, a little bit less, 73.4% hydrogen, so about 3/4 hydrogen, and 1/4 helium. Now, before this work, before the 1920s, a lot of people just assumed that the sun and the earth were made of the same material and in roughly the same amounts. The fact that the earth is mostly rocky material is what people thought the sun was too. They just thought that the rocky material was so hot that it was in a sort of gas or plasma form. So a lot of people did not believe her at the time, and it took for more follow-up observations for that to be sort of confirmed knowledge. But it was her work that was the first person to show those relative abundances. And the fact that the sun is mostly hydrogen and helium is a fact that we should kind of write down and pay attention to, because that percentages of 3/4 hydrogen, 1/4 helium is something that we're going to see over and over as we continue on in this course. As we talk about star formation and the clouds of gas and dust called nebulas that they come from, as we talk about the starting points of the universe called the Big Bang, that relative abundance of 75% hydrogen, 25% helium is going to stick around. It's going to be something we see over and over. Okay, so the sun, mostly hydrogen and helium. That's the sort of first key piece of information that we really want. The next thing that we really want to make sure that we understand and get across is that the sun is incredibly, incredibly large. It has a diameter of 1.4 million kilometers, and we've already had the lecture tutorial back from chapter 4 that shows us that it's over 100 times bigger across than the Earth. And what that means, this isn't something that we thought too hard about, the fact that it's 100 times bigger across means that if we compare the two volumes, we could actually put over 1 million Earths inside the sun if it were just like a hollow sphere. Now let's imagine that we're building a scale model of the sun. Okay, that's why this giant quarter is here on our slide. So we've all seen a quarter. Okay, we might even grab one to help us think through this scale model. So if we have a quarter, then the Earth, if we imagine 100 of them across, and that's what this little ruler is for, not trying to measure the size of the quarter, but to show that little tiny blue dot that I've drawn that kind of looks like George Washington has an earring. That little tiny blue dot is the size of Earth at the same scale. But what we really want to try to understand is starting to think about the bigger picture. We've been building up some of an understanding of just how big the solar system is in previous chapters. And that's been important because a lot of us have no real sense of how big or small space is, because it's kind of this unknowable big number that our brain can't comprehend. And so we're trying to build these scale models, and we did that for the solar system. Right? We had that one video of 7 miles of desert in order to make a scale model where the sun was about 1 meter across. Now we're going to make the sun just one little tiny quarter. Now the room that you're sitting in right now, as you're watching this video, the inner solar system could probably fit in that room. Okay, if you put 100 quarters next to each other, first of all, you'd have $25, but you'd put all of those quarters next to each other, and way out on the end of that line, you'd have the Earth. Okay, Mercury and Venus are even closer than that. Mars isn't too much further away, but maybe it's outside the room that you're in. But the outer planets would be pretty far away still, even at this smaller scale. What's more interesting, and what's really going to help us understand just how small our whole solar system is compared to the space between stars and larger. Now, if the sun were the size of a quarter, Voyager 1, which is the furthest away human-made object from the sun, it was a spacecraft that was launched in the 1970s and sent out super fast and has been going since then. With our little scale model, it's 0.2 miles away. So a couple of city blocks, you can kind of look up where the closest grocery store, maybe it's closer, maybe it's farther. But that's as far as we've had a human-made object be able to get. The Oort cloud, which we learned about when we talked about the solar system, and it's kind of the edge of the solar system, it's over 160 miles away. If you are sitting here in the Grand Rapids area, that would be the distance between here and Chicago. And that's all part of the solar system. Okay? So now we have a sense of this little tiny quarter that we're holding, and maybe we're actually holding it all the way out in all directions, 160 miles, which would include Chicago. That's part of our solar system. Okay, solar system seems quite big, but the next closest star to us, the very, very next star that we get to, is over 400 miles away. So what that means is outside of our solar system, there is nothing all the way until you get to the nearest star, which in one single direction, 400 miles away, so from Grand Rapids, that's about St. Louis, that's the next closest star, and it would be somebody holding like a nickel, because it's a slightly smaller star. So that scale model we should really try to keep in mind as we move forward, because as we start to learn about other stars, and that will be the next couple of weeks, all of these stars are incredibly, incredibly far away. That nearest star, Proxima Centauri, being way out in St. Louis, that's the single closest star to us. We still have to go even further to get to a second star outside of our solar system. Okay, so we've kind of grounded ourselves. We start to have a sense of scale. But let's bring our view back to the sun. Now this picture here from our textbook is one that after all of the lecture videos in chapters 15 and 16, we should have a better sense of and a sort of higher comfort level with. I know it might look overwhelming or scary at the moment, and maybe it would be worth kind of drawing into our notes at the end of those set of videos to kind of make sure we understand all these different terms. But this is sort of the vocabulary that we really need to have to be able to talk about what is part of the sun and what structures exist in the sun that help it power itself and help us see on a nice day. Now, we're going to spend a lot more time thinking about the interior of the sun in chapter 16 and later videos. So for now, let me just make sure we understand that when we talk about the core of the sun, it's about 20% of the interior volume. The core is actually far more dense than the outer layers, and it's in that location where the sun makes its own energy, and we'll talk about that in a later video, and where we're kind of getting that black body radiation initially, the continuous spectrum from that denser core. But above that core, there's the radiative zone and convection zone, which bring the energy and light and heat from the core outwards. The radiative zone, if you're standing near a campfire, you feel the warmth. That's radiation, that's just energy flowing out in all directions. The convection zone is physically moving that plasma, that material, up from lower down to higher up and back down again. Convection is what happens if you're boiling a pot of water. You only heat the bottom of that water, and yet all of the water gets warmed up, and that's because of convection. Convection is why the plates of the Earth, the crustal plates, move around, because the mantle has convection happening, moving it. Hotter stuff flows up, colder stuff flows back down. All of that is convection. Now the sun is so hot that it isn't actually a gas, the way that we think of steam above a boiling pot of water, but it's actually a plasma. What that means is all of the atoms, they're so highly energized they've lost their electrons. It's just nuclei without electrons and electrons without nuclei all floating around. Now the plasma, the reason that matters is it acts a lot like a fluid. If we zoomed in really, really close on the photosphere, we could see the pattern that's shown here on the top right that kind of looks almost like a beehive kind of pattern, where it's these little cells of darker outlines and lighter insides, and that pattern is called granulation. It comes from the convective motion inside the sun's interior, the same way a pot of water moves around. Now, since water is clear, you won't see this same pattern, but if you heated up a broth, like a miso soup or some other type of broth, you would actually see a similar pattern on the top of that broth as hot stuff moves up and cold stuff moves back down again. Now, remember from chapter 5 that if a object is slightly hotter, the energy it's making peaks at slightly shorter wavelengths, and that hotter object will actually produce more energy per little patch. So what we're seeing is that lighter color and the orangey part is hotter material that's just flowed upwards, and the darker outlines are all of the colder stuff that is longer wavelengths, so it's darker orange or red, and it's colder, so there's less energy per little patch. And so it looks darker to us as that colder material sinks back down again. And that's what the bottom is here to show us. You can watch the time-lapse video of this. The link is clickable on the posted slides. And it's just going to show us this in motion. It's an hour's worth of observation in just a couple of tens of seconds. Now, if we zoom out to larger scales, we no longer can see the granulation as well, but at large scales we also get to see sunspots, which are something that is really important to connect in our heads and in our notes with the photosphere. If we're talking about seeing sunspots, then we must be talking about looking at the photosphere, and that also means that we must be talking about looking in regular visible light at the ball of the sun. Again, it's not a surface, but it kind of acts like that. We cannot look any deeper than the photosphere. However, we can look above the photosphere if we use different types of light. So for example, when the moon is fully blocking the bright disk of the sun during a solar eclipse, we can actually see the outer layers of the sun all of a sudden appear because we're blocking out that much brighter photosphere. Now in this picture, which has been enhanced to show the existing structures, so they've kind of highlighted the contrast, but the pink little spikes here that you can kind of see on some of the outer edges, that's actually the chromosphere of the sun. We're going to talk about that next. And all of the other kind of lighter streaks of light around the sun is the corona. And we'll talk about that after we talk about the chromosphere. Now the chromosphere was named because of those small pinkish red spikes that we just saw. Those spikes are now called spicules. We'll see a slide of them coming up next. But that's where the name came from. If we're looking at the chromosphere, we tend to be looking at a particular set of wavelengths that are usually in the near ultraviolet. So it's highlighting plasma that is slightly hotter than the photosphere. And we'll talk about why that is in a second. But over the course of a decade, we can see that sometimes the sun is really active, and sometimes it's not so active. We'll be talking more about that solar cycle in the next video, but this is one of the images that can really highlight, if we look at this picture, in 1996 and 1997, we were at solar minimum, so the sun was kind of uniform looking when we looked at the chromosphere. In 2001, 2002, the sun was at the peak of its activity. Looking at the chromosphere, we see these active regions, these extra bright areas. If we were looking back at the photosphere, we would see sunspots. We would see lots of these sunspots, and we'll talk about why in the next video. And then when we got back to 2006, we went back to solar minimum again, where things were kind of uniform throughout. So back to those spicules. This is one of the most important parts of the chromosphere. The chromosphere and what's called the transition region, which we'll show on the next slide, are threaded with these little spikes of slightly hotter plasma that's probably an important part of the heating of the corona. Now, I say probably because it's an open question in solar physics. This is actually what I spent my work, my research in graduate school thinking about, was how to explain the fact that the corona is so much hotter than the chromosphere. So when we say this transition region, what we mean is that as we get farther away from the core, the source of energy in the sun, the temperature should drop. And that is what happens all the way up to the photosphere. So the core is at 1,000,000 degrees. By the time we get out to the photosphere, we're at about 6,000 degrees. The chromosphere has a little bit of a bump up. It's slightly hotter. Then there's a very, very narrow range of heights above the photosphere called the transition region, where the temperatures jump from about 10,000 degrees to about 1,000,000 degrees. Now, if you stepped further away from a campfire, it gets colder and colder. That's what we expect to happen. That's how physics should work. As you're getting further and further away from the source of energy, it should get colder. That doesn't happen in the corona, and what that means is there's additional processes going on that we're trying to figure out, and it's an open question that we're working on and have a lot of ideas about, but no single idea that fits all of the observations and works perfectly. Now, the corona is over 1,000,000 degrees, and so we can take pictures of the corona by using extreme ultraviolet light or by using X-rays. And then we get to see the outer layers of the sun, and that corona extends out into space a lot farther than you might think. When we talk about the corona, we're talking about a layer of the sun that has not a lot of overall material. It's very diffuse, so the opposite of dense. And when we talk about it being over 1,000,000 degrees, if we think back to the way that we defined temperature back in chapter 5, that temperature is really trying to tell us that all of the atoms and particles in the corona are just moving at incredibly high speeds. So when we talk about the coronal heating problem, or we talk about the fact that the corona is so hot, what we're saying is that the material in the corona has been accelerated to be moving at very, very fast speeds. So that corona actually extends all the way out past the Earth. So you could say that the Earth is part of the sun's corona. That material that's leaving the corona is moving at millions of miles an hour as it streams past us. There's just not a lot of that material, and we don't worry about it too much. A corona graph is how we are able to study the corona more consistently, because rather than having to wait for a solar eclipse like we saw about four or five slides ago, we can basically fake a solar eclipse by putting a disk to block the bright photosphere so that we can see those outer streaks of light that are part of the corona. Okay, so the outer parts of the sun are the photosphere. It's what we call the surface, but remember, it's not a solid surface. If we're looking in visible light, that's what we're going to see. We're going to see the photosphere. If we're looking at the chromosphere, that means we're looking at particular wavelengths that are associated with its temperature. That tends to be sort of near ultraviolet. And then the corona is seen as in extreme ultraviolet, the highest wavelengths that still are part of ultraviolet, and in the X-rays because of those very high temperatures. Now, the sun also makes what's called the solar wind, which we mentioned very briefly when we talked about comets. It's the reason why comet tails point away from the sun. But that solar wind, although it moves very, very fast, by the time it gets to the Earth, it's moving at 1 to 2 million miles per hour. It doesn't have all that much material. It's taking less than 100 trillionth of a sun every year out. Now, the link here, HelioViewer, I'm going to have us explore later, and I'll probably have it be part of office hours, kind of showing how that link works. But it is all of these different ways of exploring the observations we have of the sun in these different wavelengths, so you can kind of see how it works and see the difference between the sun at solar minimum and the sun at solar maximum. The last key term that we need to be thinking about when we're sort of building our vocabulary of parts of the sun are coronal holes. Coronal holes are not the same thing as sunspots. They have nothing to do with sunspots. If we're talking about sunspots, we're talking about the photosphere. If we're talking about coronal holes, we're talking about the solar corona. Coronal holes are places in the corona where it looks darker in images because the plasma is not trapped low down where that image is being taken. The plasma is free to flow outwards. And so coronal holes are the place where we get the fastest parts of solar wind. And the solar wind is one of many parts of what we call space weather. This image here is not to scale. It's from NASA, just kind of reminding us that there's a connection between what the sun does and what the Earth experiences, and reminds us that the Earth has a magnetic field that is protecting us from a lot of these different things. That will be part of our next video, but I'm going to wrap this up here because we've basically in this video gone through all of the key terms. If you didn't catch them, you can always reread the slides to make sure that you understood them all, reread the book, or even rewatch this video. But that's why I want to have this be its own separate thing so that we can make sure we have all those kind of terms in our vocabulary as we move forward. So I'll see you on the next section.